Good morning, everyone. I'm so excited to dive into a really crucial topic today, technical architecture. Specifically, we're focusing on non-functional components and practices. This is lesson 6 of the ICAP capstone project. It covers everything from software architecture to what we call vibe coding. It's all brought to you by ICAP Technologies.
That sounds fantastic, Sasha. I'm really looking forward to this. What exactly do we mean by technical architecture in this context? Is it different from what we've covered before?
Great question, Marina. Here, technical architecture is all about the non-functional software components. It's also about the development practices. These ensure our applications are robust, secure, and manageable. Today, we'll cover user management, role-based access control, workflow management, batch processing, and finally, version management and DevOps.
That's a lot to cover. User management sounds like a perfect place to start. Authentication is always a big topic.
Absolutely. User management is fundamental. The core idea is simple. Authenticate a user's password, then generate a secure token. That token is key. We keep it handy for all future interactions. First, in the spirit of vibe coding, let's ask Cursor to generate the user authentication code for us. On the slides, you can see how Cursor has planned it all out, from the login page to the server-side Flask code. Now, let's go into detail with the code. On the left, you see a high-level plan. Add a login page, handle the root, generate and store that token. In the center, for our server-side Flask code, we have a simple user store. Passwords are never plain text, they're hashed with SHA-256. When a user submits credentials, we hash their input. Then we compare it to the stored hash. If they match, we generate a unique, super secure authentication token. This token goes back to the client. It's a huge step for security.
That makes sense. So the token replaces the password for future requests. Does this mean passwords are never sent over the network again after the first login?
Exactly, Marina. Only the secure token is passed. This drastically reduces the risk of password compromise. It's a huge win for security. Next, let's talk client-side security in user management. While server-side is vital, the client-side truly enhances user experience. It provides initial protection and UI control. Look at the JavaScript code on the left. The isLoggedIn function simply checks for an auth token in local storage. That token is our login indicator. The Set Login button dynamically updates the UI. If you're logged in, it shows logout. Clicking it removes the token. If not, it shows login and redirects. The require auth function is fantastic. If you're not logged in, it alerts you. It can even hide or disable elements like the project grid. This prevents unauthorized interactions before a server call is even made. It makes the application feel so much more responsive.
Oh, that's clever. So the client-side check provides immediate feedback. It also stops users from even attempting actions they're not allowed to do. Is that the main benefit of this approach?
Yes, precisely. It's about immediate user feedback and a better experience. It reduces unnecessary server requests too. It's an initial filter, a first line of defense, if you will. Now, let's visualize the user management system architecture, especially server-side security. This diagram is key. It shows the browser and the Flask application server interacting. The authentication token is generated on the Flask server after a successful login. It then goes to the browser's storage. The huge benefit? You stay logged in, even if you close the browser or open a new tab. No re-authentication needed immediately. It's so convenient. From then on, that token is passed with every single request. It's like a digital key. On the server side, we use a login required decorator in Python Flask. This decorator checks for the token's presence and validity in every request. If it's missing or invalid, an error is returned. If it's valid, the function executes.
That decorator sounds incredibly powerful. So you just add login required above any API endpoint, and Flask automatically handles the authentication check for that route?
Exactly, Marina. It's super elegant. It encapsulates the security logic. This means you don't repeat the authentication check in every single function. It's a cornerstone of robust server-side security.
That really streamlines development. What about when a user logs out? Or if a token is somehow compromised? How is it invalidated?
Another fantastic question. When a user logs out, we remove the token from the browser's local storage. On the server, we can also manage a list of active tokens. If a token needs to be immediately invalidated, we can remove it from that server-side list. This prevents its future use. It's about maintaining tight control. Moving to role-based access control. First, function access control. This dictates who can view pages, create projects, or modify specific fields. Each user has roles, and each role has specific function access. It makes access control management so easy.
So roles like admin or viewer determine what buttons I can click or what pages I can even see. That's super clear.
Exactly. And those mappings are typically stored in database tables for easy management. Then, both client-side and server-side code check these permissions with every action. Then we have data access control, or DAC. This is crucial. While function access control is about what you can do, DAC is about which specific data you can read, update, or delete. Think about a project modifiable only by its creator, but viewable by all students.
So function access control is about the action, and DAC is about the data itself. That distinction is really important. How do you define those complex DAC rules, especially when it's based on multiple criteria, like in banking?
That's where it gets exciting. We can define sophisticated rules. For example, transactions in a certain geography, under a specific limit. Once defined, we generate DAC roles. These are unique identifiers representing combinations of permissions. It makes enforcement super efficient. But there's a catch, Marina. Any new or modified record needs its DAC role recomputed. If the rules themselves change, all existing DAC roles throughout the entire dataset might need to be recomputed. That can be a significant processing task. Let's go into detail on how DAC might be implemented with database tables. This really clarifies things. We have a DAC rules table. This defines field-based conditions for access. Each table needing DAC gets a DAC ID field. This DAC ID links a data record to a specific rule. Then, there's a user DAC roles table. This specifies which DAC rules a user can access. It can even include organizational hierarchy. The arrows in the diagram show how users link to rules, and rules link to data records via the DAC ID. It's a powerful filtering mechanism.
This seems really robust. So a DAC ID on a customer record, for instance, points directly to the rule that applies to it. How is this enforced efficiently in, say, a relational database?
Fantastic question, Marina. This is where relational databases shine. Enforcement is super efficient. You perform a join with the user table and organization hierarchy using the DAC ID as key. This automatically filters every SQL query. It's beautiful. The SQL query shown demonstrates this. We join customer, user, and org tables. The where clause filters by the current user's ID, their supervisors, and critically, ensures the customer table's DAC ID matches an accessible DAC ID for the user. The database handles the filtering at a very low level. This ensures consistent and secure data access every time. However, for NoSQL databases, it's different. They don't typically support complex joins in the same way. You'd likely fetch the user's allowed DAC IDs first. Then, you'd perform a separate query on the data collection, filtering by those allowed IDs. This can add complexity and impact performance compared to a single, optimized SQL join.
That's a huge distinction. So if your application relies heavily on complex data access control, a relational database might be a much better fit due to performance, or are there workarounds for NoSQL that make it viable?
You've hit on a critical point, Marina. For complex DAC, relational databases often offer a more direct and performant solution due to their native join capabilities. For NoSQL, you can denormalize data, or use application-level filtering, but it typically means more queries or more processing in your application code. It's a trade-off decision for sure. Next up is workflow management. This deals with how users progress through an application and how tasks are coordinated. We have page flow, task flow, and workflow itself. Workflow handles items multiple users need to complete, often in parallel. Think of an approval process. To make it concrete, let's look at a leave approval process. This slide illustrates a meta model for workflows. It also shows a specific workflow model for leave requests, and how it all relates to the application database. At the top, you see the simplified process flow for leave requests. An employee submits a request, it goes through, approve, reject, maybe involves emails, and finally a save or cancel. It's a very clear journey. In the bottom left, the workflow meta model is our generic blueprint. It describes core components, processes, activities, states, forms, attributes, roles, actors. It's like the language to describe any workflow. In the center, the leave request workflow model is an instance of that meta model. It's tailored specifically for leave approval. It defines activities like submit leave request, states like pending approval, and roles like applicant. It shows how a leave request progresses. Finally, on the right, the application database. Our leave request and employee tables. The workflow model describes these tables. In essence, the meta model gives us the language. The workflow model applies that language to a specific business process. The database stores the concrete instances as they unfold. It's a beautiful synergy.
That's a brilliant way to visualize it. The meta model as the language makes so much sense. Does defining these models in a structured way like this make it easier to change workflow processes later on, without rewriting a ton of code?
Precisely, Marina. That's one of the biggest wins. A well-defined workflow model, especially based on a meta model, allows for much more agile changes to your business processes. You are configuring the workflow, not hard coding every step. It dramatically reduces development time for process adjustments. It's incredibly powerful. Moving to batch processing. This is running specific code at specified times or conditions. Think of updating those DAC IDs, for example, if rules change. Traditionally, on a VPS, you'd use cron jobs. But that means continuous server costs. Modern PaaS providers like Anvil or Vercel offer scheduled background tasks. They abstract away server management. The exciting trend, though, is to limit batch processing where possible. We're moving towards real-time processing, event-driven architectures, and serverless functions. They scale on demand. It's all about responsiveness.
That makes sense for modern responsive applications. But are there still critical scenarios where batch processing is truly unavoidable, perhaps for very large datasets or complex reports?
Absolutely, Marina. You're right. While we try to minimize it, batch processing remains essential for things like large-scale data transformations. Or for complex, aggregated reporting that doesn't need to be instantaneous. Also, things like nightly data backups or system cleanups often rely on batch jobs. It still has its place. Finally, let's talk about version control and DevOps. These are absolutely critical for multi-user development and managing different environments, development, testing, production. It's how we keep everything stable and organized. For collaborative development, we use Git. The flow is, develop locally, then Git stash your changes if you need to pull. Then Git pull to get teammates' updates. Git apply stash to bring back your changes. Merge conflicts, resolve them, commit, and push. Or, be ready to roll back if needed. It's a continuous dance of integration. For build and release, it's similar but focused on stability. You pull from dev into your local build environment. Stash your changes. Pull the latest build version. Then apply your stashed dev changes. Merge. Rigorously test. If all passes, commit and push. Or, critically, roll back if issues arise. This ensures that different environments stay synchronized and stable. It's all about confidence in your releases.
That Git workflow is so important. What's the single most common pitfall you see teams run into with version control, and what's the simplest advice to avoid it?
Excellent question, Marina. The most common pitfall is not pulling frequently enough. Teams develop for too long in isolation. The simplest advice? Pull, pull, pull. Before you start work, pull. Before you push, pull. Resolve conflicts often, in small chunks. It prevents massive headaches later. It's all about continuous integration. It really helps to wipe code rapidly when your Git flow is smooth. Finally, some radical lessons from experience on making software architecture decisions. First, understand that technical architecture is almost always suboptimal. There's no perfect solution. Trade-offs are inherent. It's part of the fun. So, don't over-engineer. Future needs are rarely predicted well. Building for every conceivable scenario leads to complexity and cost. Instead, start simple. Avoid hard coding. Wrap database access in clear functions. This makes refactoring for access control easier. The wipe code rapidly concept means quickly getting a working solution, then iterating. Refactor continuously during development. Don't postpone it. Later truly never comes. Selectively use abstractions, like workflow models. Too many can add unnecessary complexity. Use them where they genuinely provide benefit. And hybrid architectures can accelerate development. Combine different technologies to leverage their strengths. Adapt as new tech emerges. It's a dynamic world.
Wow, Sasha, those are powerful insights. Refactor continuously really resonates. It's easy to push that off. And the idea of vibe code rapidly is super liberating. It encourages quick experimentation, which is key to learning and adapting.
It truly is, Marina. It's about getting hands-on, seeing what works, and building upon it. Thank you for all your wonderful questions today. This has been a fantastic discussion brought to you by iCap Academy.